And welcome to the section 10.2 video lecture for Math 141 Statistics at Morton College. Once again, I am your instructor, Dr. Scott Spaniel, and today what we're going to do is talk about hypothesis tests for a population proportion. So in the section 10.1 video, we talked about the general idea of how hypothesis tests work and why we do hypothesis tests, but the part we left out was the middle part, how to decide whether or not to reject or not reject the null hypothesis. So that's what we're going to look at today for population proportions, because the work's slightly different depending on what type of parameter you're working with, but is fairly similar. So you can go ahead and take out your chapter 10 handouts, and we'll go ahead and take a look at those. So, when observed results are unlikely under the assumption that the null hypothesis is true, we say that the result is statistically significant. When the results are found to be statistically significant, we reject the null hypothesis. So what we're trying to do with the inferential statistics we're doing in this section is show that what we found is either unlikely or not unlikely, given that the null hypothesis is true. And if we find that it is unlikely, then we can reject the null hypothesis and then go from there to write our conclusion like we talked about in the last section. And we're going to practice doing all of that today. So there are a few different approaches you can take for hypothesis testing, but far and away the most common one is what's called the p-value approach. And so for this class, we're going to focus on that one. I think it's also the easiest one to understand, which is a happy plus that goes along with that. So assuming that H0 is true, if the probability of getting a sample mean as extreme or more extreme than the one obtained is small, we can reject the null hypothesis. So the idea is what we're going to do is we're going to use the information we learned in chapter 8 to find probabilities, assuming that the null hypothesis is true. And if our probability is low enough, then we can reject the null hypothesis. And we'll talk, so that's the idea of what we're looking at. So to test hypothesis regarding the population proportion, we can use the following steps, provided that we can use the sample proportion distribution that we talked about in chapter 8. And to do that, we have to remember a few things to get that distribution. So the sample is obtained by simple random sampling. We need to have this be a normal curve. So we need n times p0 times 1 minus p0 to be greater than or equal to 10. And the sample values need to be independent of each other, which, remember, we can show that they're independent of each other by showing that n is less than or equal to 5% of the population, so less than or equal to 0.05 times capital N. So assuming those things are true, then we can do the following steps. So the first thing we do is we determine the null and alternative hypotheses, like we talked about in the last section. The hypotheses are structured in one of the following three ways, right? Either the null hypothesis is always the same. It's p equals whatever our p0 was, whatever value we're starting with. And then our alternative hypothesis is either the values are not equal to each other, it's gone down, it's less than, or it's greater than. So changed, decreased, increased. So then we select a level of significance alpha depending on the seriousness of making a type 1 error, and this alpha is going to be our cutoff point for the probability we're going to calculate. We want the probability to reject the null hypothesis based on this. So then we're going to use technology to determine the p-value, and that's what we'll look at today. In our case, technology is going to be ClassCalc. Okay, so for us, we're going to use ClassCalc. And then if the p-value is less than alpha, we reject the null hypothesis. If it's not less than alpha, we do not reject the null hypothesis. So just to practice going through this, I went ahead and gave us one where we have the alternative and null hypothesis, and I just want to show you how to use the calculator to do this. Okay, and so in this case, we're dealing with one variable, we're dealing with proportions, and we're doing a test on the normal curve. So we're going to use what's called one prop z-test. So in ClassCalc, we're going to go to Stat, Tests, and we're going to choose one prop z-test. Notice this is exactly the same wording as one prop z-int, except we're doing a test instead of an interval. So we're going to choose one prop z-test. And you could type it out just like that, and it'll pop up. And then it's asking for three things. It's asking for P naught, which is the value of the null hypothesis, X, which is the sample success count, and N, which is the sample size. So if we look back at our problem, we've got our P naught is this value in the null hypothesis and the alternative hypothesis. We've got our X is 75 and our N is 200. And so we just put those values in. So 0.3, X is 75 and N is 200. And then notice what it'll show us here is it'll find the p-value for all three possible hypothesis tests. So in our calculator, it's telling us less than is 0.9897, greater than is 0.0103, and not equal to is 0.0206. And then it's also telling us that Z is 2.3145 and P hat is 0.375. Okay, so those are all the values it gives you. Okay, so let's talk about what those values mean. Okay, so these are the three different hypothesis tests. So for this, these things up here are the three different hypothesis tests. So you want to pick the one that matches your alternative hypothesis. And so in this case, that's this one. Okay, so that's the one we'll use. These two are fine. We just won't use them for this problem. Okay, this value, the Z, is called the test statistic. So that's the z-score of our data value. So that's our z-score of x divided by n. And then this is x divided by n, p hat, right? That's the value you get. So that's the point estimate, which in this case is the sample proportion. Okay, so those are the 5 values that you get when you use ClassCalc to do this. And you may or may not need them on the problems. This one that's in the box is the one we need to determine whether or not we're going to reject the null hypothesis. The other ones are things they might ask you for on the homework. So in this case, our p-value is 0.0103. And so the question is that less than our alpha, which is 0.05? And in this case, it is. So therefore, we can reject the null hypothesis. And then we can write a conclusion based on what our hypotheses are. Okay, so that's the testing part that goes in the middle here that we didn't talk about in the last section, how to do the actual test. So now let's put it all together. The stuff from section 10.1 and this. So what we're going to have now is we're going to have some problems here on the next 2 pages where we're going to look at how do we write the hypothesis, do the test, decide to reject or not reject the null hypothesis, and then state a conclusion. So in August 2003, 56% of employed adults in the United States reported that basic math skills were critical or very important to their job. The supervisor of the job placement office at a 4-year college thinks this percentage has increased due to increased use of technology in the workplace. He takes a random sample of 480 employed adults and finds that 297 of them feel that basic mathematical skills are critical or very important to their job. Is there sufficient evidence to conclude that the percentage of employed adults who feel basic math skills are critical or very important to their job has increased at the alpha equals 0.05 level of significance? Okay, so I tried to, as I was reading that, I tried to underline the important information. So first of all, this 56 is the current number. So that's our P naught. So when I'm writing my hypotheses, we're going to have P equals 0.56, and then we're going to have P something 0.56. And then we have to decide which inequality symbol goes there based on whether we're changing, increasing, or decreasing. In this case, we're increasing, so that's going to be the greater than symbol. And once again, you don't necessarily need to know what that is to run the hypothesis test. You need that to know which one of the hypothesis test results am I going to use. So in this case, that's greater than. And then we need x, n, and alpha, right, to be able to run x and n to be able to run the test. So our x is 297 and our n is 480. And so now we can run the hypothesis test. So you could go into the menu again, or if you just start typing 1 prop z test, should pop up. I don't know why it added that. So, there's probably a shorthand I can use for it. Let's see. 1 prop z test. Yeah, so if you type in OPZT, it brings this up. Or you can find it in the menu. So our P naught was 0.56. Our X is 297. And our N is 480. And so in this case, we choose the answer. We get less than is 0.9952, greater than is 0.0048, and not equal to is 0.0095. I don't need the test statistic or p-hat, but if you wanted them, they're also given right there, right? And so then you just have to pick the correct inequality here. The one that matches what we're doing is greater than. So this is going to be the one we're using. So we won't use these other two numbers. So our P is 0.0048. And we want to know, is that less than alpha, which is 0.05? And in this case, 0.048 is a lot less than 0.05. So it is that. So that means we reject the null hypothesis. And then as we saw in the last section, we can write a conclusion based on that. So in this case, we can say there is sufficient evidence to suggest the alternative hypothesis, which in this case is to suggest more than 56% of employed adults feel basic math skills are critical or very important to their job. Okay. And so that's the idea. So all that's new here in this section compared to the last section is this stuff in the middle, deciding whether or not to reject the null hypothesis. Okay. So let's go ahead and try another one together. So the second one says, in 1994, 52% of parents of children in high school felt it was a serious problem that high school students were not being taught enough math and science. A recent survey found that 256 of 800 parents of children in high school felt it was a serious problem that high schools were not being taught enough math and science. Do parents feel differently today than they did in 1994? Use alpha equals 0.05 level of significance. Okay. So in this case, our null hypothesis, right, is going to be that P equals 0.52%, because that's 0.52, not 0.52%. 0.52, which is the same as 52%, because that's what the current value is. That was the previous value. That's the null hypothesis. And the alternative hypothesis, in this case, do they feel differently today? So that would be not equal to 0.52. Okay. And then we have an N value, an X value of 256 out of a sample of 800. So we can do a 1 prop z test with those values. So 0.52, 256, and 800. Now, this is the interesting thing, is notice these values. We got 0 for less than, 1 for greater than, and 0 for not equal to. Now, most likely what that means is this is not actually 0, but it's so close to 0 that it got rounded off to 0. So in this case, our p-value for not equal to is 0, which is indeed less than our alpha of 0.05. Right? And notice this z-score. Our data set was 11 standard deviations below the mean. So it's way down there below the mean, which makes me think there's probably a typo in this problem. But anyway, it still works. We still did the test. And it still lets me talk about our 0. So it doesn't actually have a probability of 0. It's just so close to 0 that it got rounded off. So in this case, once again, we could reject the null hypothesis. And then we can write a conclusion just like in the last section. So in this case, we could say there is sufficient evidence to suggest the proportion of parents who believe their children, or not necessarily their children, but believe high school students are not being taught enough math and science has changed since 1994. Probably need to update this problem because I'm guessing at least some of you watching this video weren't even born in 1994. So I could probably get a more up-to-date question. But anyway, so that's the idea. And like I said on the previous problem, all that's different is this middle part here, right? Doing that and deciding whether or not to reject the null hypothesis. So why don't you guys pause the video for a second and try these two problems on page 10. Okay, so now that you've had a chance to try them, let's go through them together. So in February 2008, the Gallup organization surveyed 1,034 adults between the ages of 30 and 64 years of age and found that 54 were worried that they will outlive their money after they retire. Does the sample evidence suggest a majority of 30 to 64 year olds in the United States are worried they will outlive their money? Use the alpha equals 0.05 level of significance. So there's a little bit of a trickiness to this one that we haven't talked about yet, but I think I mentioned this way back in an earlier video, which is, what does the word majority mean? Well, the word majority means more than 50%. So in this case, our null hypothesis is going to be that P is 50%, so 0.5, and our alternative hypothesis will be that P is greater than it, okay? That we have a majority. Okay, so we'll assume we don't, and then we'll try to show that we do have a majority. In this case, our X is 548, and our N is 1,034. And so now we've got all the information we need in order to go into the calculator. And we can put in what we have, so 0.5, 548, and 1,034. In this case, we're looking at greater than, so our p-value is 0.0269. Okay. So the question is that less than our alpha? And once again, it is. Hopefully I got at least one example where it's not. But once again, it is, because that's about 3%, which is less than 5%. So we can say, we can reject H naught and say there is sufficient evidence to suggest a majority of adults age 30 to 64 are worried they will outlive their money. Okay. Okay, so that's that one. So now the second one, here's similar idea. So it says in 2000, 58% of females age 30 15 or older lived alone, according to the U.S. Census Bureau. A sociologist tests whether this percentage is different today by conducting a random sample of 500 females aged 15 years of age or older and finds that 285 of them are living alone. Is there sufficient evidence at the alpha equals 0.01 level of significance to conclude the portion has changed since 2000? Okay. So P equals 0.58 is our null hypothesis. Our alternative hypothesis, we're doing change, so that's not equal to 0.58. Okay, so now we can do the calculation. So 0.58, and I forgot to write down the other ones. We know from the sample that X is 285. X is 285, and N is 500. And so in this case, we get our p-value, since we're doing not equal to, is 0.6505, which is not less than alpha. Right? So, because it's not less than alpha, we do not reject H naught, and therefore we can say there is not sufficient evidence to suggest the null hypothesis. So there is not sufficient evidence to suggest the proportion of females living alone has changed since 2000. Okay. So that's the idea of how to use this one prop z-test. Now, one of the things I skipped over a little bit with all of these is the idea that I didn't check to make sure I actually could do a hypothesis test. And the reason I skipped over that is because all of these p-values were pretty close to 50%, and all our samples were really big, and all our populations were really, really big. So I didn't really need to check any of these things. But that is a good habit to get into with checking these, and we'll talk about why later on in the video. But just know that for all of these examples that we just did, all three of those requirements were met. Okay, another option that we want to throw out here is the idea of do two-tailed hypothesis testing using what we talked about in Chapter 9 with confidence intervals. So when testing P equals P naught versus P does not equal P naught, if a 1 minus alpha times 100% confidence interval contains P naught, we do not reject the null hypothesis. However, if the confidence interval does not contain P naught, we conclude that H1 is true at the level of significance alpha. So the idea here is a confidence interval is where we expect P naught to fall. So if it falls within that interval, we're like, oh, that's where we expect it to fall. But if it doesn't fall within that interval, we're like, oh, something's up here. We reject the null hypothesis, and we assume the alternative hypothesis is true. So to give you an example of that, a June 2007 study conducted by Students Against Destructive Decisions, SAD, revealed that 37% of teens aged 16 to 17 years of age text while driving. Does a 2009 study by the Princeton Survey Research Association International, which found that 272 of 800 randomly selected 16 to 17-year-olds had texted while driving, provide enough evidence that the proportion of teens who text while driving has changed since 2007? And it occurs to me that I left out something here at some point. Let's call alpha 0.05. 0.05. I don't think one's given here. I don't see it. So we'll 0.05 is fairly standard, so we'll use that. Okay, so we start the same way. We write our hypotheses. So in this case, P equals 0.37, and P does not equal 0.37, right? Because we're doing changed. And because we're doing changed, that's what allows us to use confidence intervals. If we weren't doing changed, we'd have to use a hypothesis test to do left-tailed or right-tailed tests. Okay, and then our X is 272, and our N is 800. Okay, so we can go into ClassCalc, and instead of doing one prop z test, we can do one prop z int, which I can one, and we can put in our x, which is not point anything, is 272, and our n, which is 800, and then we have to give it a confidence level, which our confidence level, right, is 1 minus alpha times 100%. So in this case, that'd be 1 minus 0.05 times 100%, which is 0.95 times 100%, which is 95%. Or in ClassCalc, we have to put it in as a decimal anyway, so it's really just 1 minus alpha, so 0.95. Okay, and that gives us our confidence interval. So our interval here is 0.307 to 0.372. Okay, so now the question is this value 0.37 in this interval? And if so, is it between those two numbers? And the answer is yes. 0.37 is in the interval. And because it's in the interval, that's what we expect to happen, right? We expect the population proportion to fall within our interval. So therefore, we would not reject H naught. And so we could write a conclusion like there is sufficient evidence, or there is not, sufficient evidence to suggest the alternative hypothesis. In this case, to suggest the proportion of teens who text while driving has changed. Okay, and so that's the idea. So you can do two-tailed hypothesis test using confidence interval by simply saying, is your P0 value in the interval around your sample data or not? So go ahead and pause the video for a second and try doing this second one. Okay, so now you've given it a try. Let's go through it. So according to menstuff.org, 22% of married men have strayed at least once during their married lives. A survey of 500 married men results in 120 indicating that they have strayed at least once during their married life. Construct a 95% confidence interval for the population proportion of married men who have strayed. Use this interval to assess the accuracy of the statement made by menstuff.org. Okay, so our null hypothesis is that P equals 0.22, and our alternate hypothesis, because we're doing it tells us to construct an interval, is not equal to 0.22 with an x of 122 and an n of 500. Okay, so we put in the information it asked for. So x is 122, n is 500, and our confidence level is 95%, so 0.95. And so we get a confidence interval of 0.21 to 0.28. Okay. And so we look at that and we ask, is 0.22 in this interval? It is. So 0.22 is in the interval. So we do not reject the null hypothesis. So there is sufficient evidence, or there is not sufficient evidence to suggest the proportion of married men who have strayed at least once is not 22%. Okay. So that's the idea. So that's just another, with these two-tailed tests, another way to go about it. Now the last thing in this section is, well, what happens if I do my test and I get that n times p naught times 1 minus p naught is less than 10. Is there a way that I can still do a hypothesis test here? I can't use the normal curve because we don't have enough evidence to suggest that this is normally distributed, but is there another way about it? And the answer to that is, well, there can be. If you're doing a right-tailed test or a left-tailed test, what we can do is use the idea of binomial. Because in all these cases, when we're doing these, we have an x value and we have an n value. So we have a number of trials n and a number of successes x, which is all we really need to do in order to do a binomial probability. So for right-tailed tests, what we want to do is we want to find the p-value is the probability of obtaining x is greater than or equal to p naught. And for left-tailed tests, it's the p-value is the probability that x is less than or equal to p naught. If the p-value is less than the level of significance alpha, we reject the null hypothesis just like all the other ones we've done before. Okay, so let's look at a couple of examples of this. So according to the U.S. Census Bureau in 2000, 9.6% of Californians had a travel time to work of more than 60 minutes. An urban economist believed that the percentage of Californians who have travel time to work of more than 60 minutes has increased since then. She randomly selects 80 working Californians and finds that 13 of them have a travel time to work of more than 60 minutes. Test the urban economist belief at the alpha equals 0.1 level of significance. Okay, so start out by writing your hypotheses. So P equals 0.096, H1, P, she thinks it's increased, so 0.0, P is greater than 0.096. Now in this case, if we take N, which is, and then our X is 13 and our N is 80. If we take N times P naught times 1 minus P naught, we get 80 times 0.096 times 1 minus 0.096. So we can bring that up on the calculator here. So 80 and we get 6.94, which is not greater than or equal to 10. Right? For some reason I wrote twice. Which is not greater than or equal to 10. So therefore we can't use one prop z test or one prop z int. So that means now though we can do binomial. Okay, so if you remember back in chapter 6, we talked about the binomial probability distribution. So if I go into stat, distribution and plot and choose binomial distribution, notice what it wants is n and p in order to get the distribution. And we know n and p, right? We know that n in this case is 80, and we know that p is 0.096. Right, and there's my binomial, and you can see that while it's close to normal, it's not normal, right? It's a little more skewed to the right. So now what we can do is we want to know what is the probability of getting more than 13 successes. Okay, so in this case, we're looking at an x of 13. So what is the probability that x is greater than or equal to 13? That's the probability we want to find. Okay, that many successes. So we can do that, right, by just doing CDF and doing x, 13 is less than or equal to x, right? And so now we've got to the right that way. So we get 0.0410. And now that we've got our probability, the rest of the problem is just like the ones we've been doing today. So this is that less than alpha, which is 0.1? The answer to that is yes. So we reject H naught, and then we can write a conclusion. So we can say there is sufficient evidence to suggest H naught, H1. And notice I shorthanded that because I'm running out of space, and this is a pretty long video already. But in general, in the homework, you're just going to be choosing multiple choice. And if you were writing these out, if you have to write these out by hand, then you would want to write out what is H1. If you shorthand it, that's not really right, but I need to because I'm running out of space. Okay, so let's try another one together. Okay, so the second one here says, according to the U.S. Census Bureau, in 2000, 1.5% of males living in Colorado were teachers. A researcher believes that this percentage has decreased since then. She randomly selects 500 males living in Colorado and finds that 3 of them are teachers. Test the researcher's belief at the 0.1 level of significance. Okay, so we're going to do the same thing. So H naught is going to be P equals 0.015. H1 will be that P is less than 0.015 because we think it's decreased. X is 3, N is 500. And if we check 500 times 0.015 times 1 minus 0.015, we get 7.39, which is not 7.39, which is not greater than or equal to 10. So we can't use one prop z-test, so we want to use binomial distribution to find the probability that x is less than or equal to 3. Right, because we're doing less than, so I want to do less than or equal to 3. So I can go in here, do a binomial distribution. My N is 500, right? That's my sample size. My P was 0.015. So there's my distribution. Once again, notice it's close to normal, but it's a little skewed right. So that's why we couldn't use one prop z-test. And then we want to do, in this case, x is less than or equal to 3. Okay, and we get 0.0578. So this is a good example of when it's really important what alpha you're using. If alpha was 0.05, I wouldn't be less than alpha. But in this case, because it's 0.1, I am less than alpha, so I would reject H naught. And that's why it's really important that you set your alpha at the beginning of the problem before you do any of the work. To avoid bias, because it could be really, really close. In this case, it kind of is. So here we would reject it, and then we could say there is sufficient evidence to suggest that the percentage of males living in Colorado that are teachers has decreased since 2000. Okay? So take a minute, go ahead and pause the video and try this last one. Okay? So now that you've had a chance to try it, let's run through it together. So according to the U.S. Census Bureau, in 2000, 3.2% of Americans worked at home. An economist believes that percentage of Americans working at home has increased since then. He randomly selects 150 and finds that 8 of them work at home. Do, is what that should say, a higher proportion of Americans work at home. Okay, so H naught would be P equals 0.032. H1 is P is greater than 0.032 because he thinks it's increased. Our X is 8. Our N is 150. Our N times P naught times 1 minus P naught gives us 4.65, which is not greater than or equal to 10. So we have to use the binomial distribution. So we do our binomial distribution here. With an N of 150 and a P of 0.032. And you can see if we zoom in on this one's even more skewed than the other ones. And we want to know if it's increased, so we're going to do the probability that X is greater than or equal to 8, greater than or equal to the value we got. And so for this one, we get 0.1099 for our p-value. So is that less than alpha, which equals 0.05? No. So therefore, we would do not reject H naught, and we would say there is not sufficient evidence to suggest that the proportion of Americans who work at home has increased since 2000. Now, I'm guessing if we redid this study today, that answer would go way up, but at the time that he did his sample, that was not the case. Okay, so that's it for section 10.2. Next time we'll talk about doing the same idea with means. And always is if you have any questions, feel free to shoot me a message on Remind or by email. And make sure you're doing your homework and your quizzes. And we'll see you for the next video.